Our topic is nanoparticles and energy storage. Our group members are Alex Kluge, Brandon Yuan, Luke Brandes, and Sebastian Pritchard. So, what type of nanoparticles were used? The type of nanoparticles used in this experiment are beta cobalt hydroxide nanoparticles. They were prepared by pulse galvanostatic electrodeposition from a nitrate bath. These nanoparticles form a brucite-like phase of cobalt hydroxide, and they appear in a hexagonal crystal structure. The nanoparticles are also ultrafine particles with sizes smaller than 5 nanometers. The nanoparticles are well dispersed throughout the solution, and additionally, they were found to have porous morphology. These factors work together to create excellent energy storage ability for the nanoparticles. They also showed high specific capacitances of 1070.5, 906.4, and 801.3 farads per gram at densities of 1, 3, and 5 amperads per gram, which further shows their high energy storage abilities. And then finally, the transmission electron microscope and the scanning electron microscope images of the nanoparticles are shown on the right. The hexagonal structure and well dispersion can be seen through these images.
All right, so what is the application of these nanoparticles? In the experiment, the prepared nanoparticles of beta cobalt hydroxide yielded two very important results, being that, first of all, there was a very high specific heat capacity that therefore translates into a greater capacity for energy storage. And the second important result being that the specific heat capacities were very consistent, meaning that throughout testing in the charge and discharge cycles, it proved that the heat capacities of these nanoparticles were very consistent, which means that the reinforcement of the nanoparticle research proves that they have the potential to create overall more efficient energy storage, which is proven in the figure as the high transmittance value equates to a high light transmitted and therefore a higher energy capacity. It has the potential to improve the density of energy in batteries due to, again, the unique nanomaterial properties, such as the very high surface area. It has the potential to improve the speed of charging/discharging as shown in the test in the experiment due to the rapid energy transferring capability of nanoparticles. Has the potential to reduce weight of energy storage devices, again, because they are more efficient, contribute forms of energy storage that are more sustainable in our environment once the nanoparticle engineering process is finished, contribute to the creation of other nanomaterials that can be used in other forms of chemistry and engineering, and contribute to the development of redox flow batteries, which again, nanoparticles will improve the efficiency.
So now we'll look at how the nanoparticles are actually involved in the application. It's primarily the physical properties of the particles that allow them to be viable for energy storage, such as their size, surface area, and structure. The absorption-desorption behavior was also observed. It was concluded that the particles are microporous. And if you look at the small graph off to the right, it compares pore diameter to and pore volume. And the average pore diameter was approximately 3.2 nanometers, which is right in that sweet spot where the pore volume is the highest, which leads to a high absorbed volume as well. So overall, the standout attributes of the cobalt hydroxide particles are the ultrafine and microporous nature, as this greatly increases surface area, which in turn increases their energy storage ability. All these factors, along with well dispersion, led to the particles having extremely high specific capacitances, as well as long-term stability. And an example of that stability is that the nanoparticles were able to maintain nearly 90% of their initial charge capacity after 500 charge-discharge cycles.
So what current technology method is this improving upon? So according to experiment results, it concluded that the cobalt hydroxide nanoparticles deliver energy and power densities, which indicate its excellent energy storage ability. The nanoparticles showed high specific capacitances at multiple current densities, so that further confirms their excellent energy storage ability. So what does this mean? This improves upon current technology in lithium-ion batteries because it provides consistent excellence when it comes to energy storage at common current densities. In a similar manner, according to Figure 5, as you can see, the nanoparticles exhibited an excellent long-term stability in which they were able to deliver on average 91.83% of their initial capacities after 500 charge and discharge cycles. This discovery is also greatly beneficial to lithium-ion battery technology because this paves the pathway for more efficient, longer-lasting batteries. Not only does this improve the quality of lithium-ion batteries, but with longer-lasting batteries, there will also be less pollution and waste since they are not being thrown away as often. Altogether, the discoveries made on the cobalt hydroxide nanoparticles pave the path for sustainable energy sources that reduce global pollution. Additionally, the energy storage ability of the nanoparticles can improve batteries by giving them a longer lifespan, more efficient energy delivery, and consistent energy capacity. By making these improvements to lithium-ion batteries, our current day technology will see great improvements. The better, greater lithium-ion batteries will allow engineers and developers to have more room to push our technology to the limit, and thus we will be able to see great innovations from the discoveries made on the cobalt hydroxide nanoparticles.
This is our source that we use to get all of our information that presented in the slideshow. And then we wanted to end with a quote. Nanotechnology will let us build computers that are incredibly powerful. We'll have more power in the volume of a sugar cube than exists in the entire world today. Quoted by Ralph Merkle.